Hello everyone, and welcome to another lecture. Today we're going to talk about combinations, but before we do, we're going to talk about a topic that we just finished up in the previous lecture, and that was the topic of permutations. Remember, a permutation of a set of objects is an ordered arrangement of the set of objects. With a permutation, order matters. Specifically, we might be interested in the number of permutations of R objects selected from a set of N objects. This is how we denote that. And what we're going to do is we're going to select R objects from a set of N objects. And the order of selection matters. So we want the number of permutations of R objects selected from a set of N objects. And the classic example here is a horse race with 10 horses running. Suppose we want to compute the number of 1, 2, 3 finishes of a horse race in which 10 horses are running. And remember, in a horse race, order matters. For example, if horse number 10 finishes first, and horse number 3 finishes second, and horse number 5 finishes first, that's a completely different outcome than if horse number 5 finishes first, and horse number 10 finishes second, and horse number 3 finishes third. These are completely different outcomes because order matters. The first place horse is going to pay more money than the second place horse. And the second place horse is going to pay more money than the third place horse. And none of the other horses are going to pay a cent. So order matters. If we bet on a horse, it's good that our horse is in the top 3, but it's even better if our horse is first. Order matters. So in a horse race, the order in which the top 3 horses finish matters. And how many different ways can 10 horses finish in the top 3? How many different 1, 2, 3 finishes can we get from a field of 10 horses? We're looking at the number of permutations of 3 horses selected from a set of 10 horses. Order matters. Now suppose order doesn't matter. The only thing that matters is whether an object's selected or not. And the order doesn't matter. Are there any really good examples of a case where we're selecting R objects from a set of N objects and the order of selection doesn't matter? If the order does matter, then it's a permutation. And the classic example to illustrate a permutation is a horse race and the number of 1, 2, 3 finishes. But what if order of selection doesn't matter? We're just selecting R objects from a set of N objects, and the order in which the R objects is selected doesn't matter. Suppose we want to compute the number of ways that we can select R objects from a set of N objects, and the order doesn't matter. How would we do that? And is there a classic example where we select R objects from a set of N objects and the order of selection doesn't matter? What do you think? Is there a classic example? We'll find out in just a minute. Suppose that we have a set of N objects and we select R objects from this set. If the order of selection is irrelevant, then we are selecting a combination of R objects from a set of N objects. If the order of selection is irrelevant, then we are selecting a combination of R objects from a set of N objects. The number of combinations of R objects selected from a set of N objects is denoted NCR. And you may have a button on your calculator that computes this. Check it out and see. But this is the number of combinations of R objects selected from a set of N objects. And this is how the number of combinations of R objects selected from a set of N objects is computed, in case we don't have that button on the calculator. Notice that here we have capital C for combination. If this were a permutation and the order of selection mattered, this would be a capital P. But if the order is irrelevant, it's a combination, and we have a capital C here. Now, how about it? Can we think of any event where we're selecting a set of R objects from a set of N objects and the order of selection doesn't matter? What about jury duty? That we have a pool of jurors, and from that pool we're going to select 12 jurors. Does the order of selection matter? It doesn't, does it? The fact of the matter is, either a person is on the jury or they're not on the jury. If they're on the jury, it doesn't matter whether they were the first or the last selected. They're one of the 12 jurors. So the classic example for a combination of R objects selected from a set of N objects is the selection of jurors for a jury. Here's a classic example. Selection of a 12-juror jury from a pool of jurors. Order of selection doesn't matter. A juror is either on the jury or they're not. Compute the number of juries with 12 jurors on a jury that can be selected from a pool of 50 jurors. Order of selection doesn't matter. This is a combination. So we want the number of ways that 12 jurors, the number of combinations of 12 jurors selected from a set of 50 jurors. And that's going to be 50 factorial over 50 minus 12 factorial times 12 factorial. wonder what that turns out to be. I just cranked it out. Here's what it is. Nope, I'm not done yet. From a pool of just 50 jurors, if we select 12 jurors, order of selection irrelevant, doesn't matter, there are 121,399,651,100 different 12-juror juries that we can select from a pool of 50 jurors. Who on earth would have thought it could have been that high? Let's do some practice computations, computing things like this. Let's do a few problems. And in this session, I will mention something that I had overlooked unforgivably, actually. Right now, when you do your exercises in MyMathLab, they give you facilities where you can use factorial and combinations and permutations. But on your final exam, you're going to have to use the TI whatever calculator. And you're going to have to know how to find factorials and permutations and combinations on that calculator. So let's compute a few of these. And I'll also talk about how we do these things using a calculator. Here we want the number of combinations of a set of 2 elements selected from 7 elements. And in terms of factorials, this is 7 factorial over 7 minus 2 factorial times 2 factorial. Holy moly. 7 factorial, let me write down what I got for this. Now let's see. When I crunched all of this, I got 21. But let's talk about how we do this on our TI whatever calculator that we're going to be using in the final exam. We should probably practice some of this right now and not wait until a couple of days before the final exam to learn how to do this. So in order to do something like this, we type 7. And then we'd hit this key, the probability key on the calculator. And here's what we're going to see. We're going to see NPR, NCR, and we're going to see factorial. And when we first hit the PRB button, NPR is going to be underlined. Well, we don't want NPR, we want NCR. So what we do is we hit the right arrow button on our calculator. And what that will do, it will move the underline from here to here. And what we'll see is NPR, NCR, underlined, and factorial. We'll hit enter. And then we'll type the other number 2. So the first thing we do, type the 7. Then hit the probability key. That will take us to a screen where it lets us select one of these 3. With the right arrow button, we'll move the underline to underline NCR. We'll hit enter. And on the screen, what we should see at this point is 7 NCR. And we type in 2. And hit enter. Let's see, did I fit all of that in? By golly, I sure did. So when we use our TI calculator for the final, this is how we'll do it. And we'll get 21. If you have your calculator, you may want to try doing that right now, just to get comfortable with it. We don't want to wait until the night before the final exam before we take out our calculator and say, oh my God, how do I compute combinations and permutations? Uh, 12 factorial. When we do the exercise in MyMathLab, they'll have a factorial symbol down at the bottom of the screen that you can use. Suppose we wanted to do this on a calculator, particularly the calculator that we're going to use for the final exam. We'll type 12. And then we'll hit the probability key. And this is what we're going to see. We're going to see NCR, and it's going to be underlined. We're going to see NCR, and we're going to see factorial. Is that showing up? I guess it is. And what we do is we hit the right arrow key twice. And that's going to move the underline from here to here to here. And what we will see is NCR, I'm sorry, the first symbol is NPR, forgive me please. NCR and factorial. When we first hit the probability key, we'll see NPR underlined. We'll also see NCR and the factorial symbol. We hit the enter key, the right arrow key twice. That moves the underline from here to here to here. So the factorial will be underlined, and that's exactly what we want. And so we'll hit the enter key. And we'll get whatever 12 factorial is supposed to be. Maybe I should check out what it is and get back to you. Okay, if we did this correctly, 12 factorial, we got 479,001,600. Let's try another example with factorial using our TI calculator. the one we're going to use for the final. 9 factorial using our TI calculator. We'll type 9. We'll hit the probability key. And NPR will be underlined, but we want factorial. So we'll hit the right arrow twice. And that will move the underscore from NPR to NCR to factorial. We have factorial underlined, and that's what we want, so we'll hit enter. And we should get 9 factorial, which is 362,808. Now let's do some more combinations and permutations. Compute 7C2, the number of ways that 2 combinations can be selected from a set of 7 elements. And here's what we do. Type 2, and we hit the probability key, PRB, and we're going to see NPR underline, NCR, and we're going to see the factorial. We want factorial, so we'll hit the right arrow key twice to move the underscore from NPR to NCR to factorial. And so this is what we should see now. NPR, NCR, and factorial with an underscore. Oh, that showed up pretty well, didn't it? Okay. We have the factorial underlined. Holy moly, we don't want factorial, do we? We want combinations. Okay. And 2 is not the first number either, is it? Okay. Let me do this again, because I have really mucked this one up. We want 7C2, so I should enter 7, hit the probability key, and when I do, the NPR key will be underlined. But I don't want a permutation, I want a combination. So I'll hit the enter key once to move the underscore to the NCR key. And when I do that, we'll still get this pretty blue color. But this time, the NCR key will be underscored. The thing that we want has the underscore, and so we'll hit enter. And now is the time to enter or type 2. And after we type 2, we'll hit enter. And 7 choose 2, son of a gun. We should get 21 as an answer. One more example, but let's do the permutation this time. Compute the number of permutations of 2 elements. Is that what I want? I don't think so. do something a little bit more challenging. The number of permutations of 3 elements selected from a set of 10 elements. And if we're doing this in factorials, we're going to have 10 factorial over 10 minus 3 factorial. And when we hit enter, we're going to get 720. But suppose we use the NPR function in our calculators. We want 10p3. We type the first number, 10. We hit the probability key. And on the screen, we see NPR, NCR, factorial. This time, we want the permutation, NPR. So we just hit enter. And all we have to do after that is type the next number. And we hit enter again. And when we do, we get our answer, 720. Practice doing some of these exercises using the calculator so that when we take the final exam, we'll be very comfortable using the TI calculator. We don't have to spend hours and hours doing this, but get comfortable doing it now so that when we take the final exam in about 3 weeks or 4 weeks, we'll be comfortable using the calculator. And it's not something that we'll have to struggle to learn the night before we take the final exam. Matt has 12 shirts, and he must choose 4 to take with him on a business trip. How many different ways can Matt select 4 shirts? Question mark. Now, is this a combination or is it a permutation? Does the order in which the 4 shirts are selected matter? No. Either he's taking a shirt on the business trip or he's not. Either he's selected one of these shirts or he hasn't. Order is irrelevant. So this is a combination. We want the number of combinations of 4 shirts that can be selected from a set of 12 shirts. And if we do this factorial-wise, this is 12 factorial over 12 minus 4 factorial times 4 factorial. And I think that gives us, what? What did I compute this to be? 495. Or we can use the combination function, 12 combination 4. And we'll enter 12, hit the probability button on our calculator, move the underscore to underline NCR and hit enter, and type the 4, and hit enter, and we'll get 495. Let's do this one. The senior class of Wood River Junction High School is electing class officers. Each of the 100 members of the class will vote for one of their classmates. The top vote getter will be president. The second top vote getter will be vice president. Third top vote getter will be secretary. Fourth top vote getter will be treasurer. fifth top vote getter will be social chairman. 5 officers will be selected in this manner. How many possible ways can the 5 officers be selected? And if we think about this, isn't this going to be a 1, 2, 3, 4, 5 finish? Only the first 5 finishers matter and order matters. The first one will be president. The second will be vice president, and so forth. So order matters in this case. Order of selection matters. This is a permutation. We're selecting a permutation of 5 people from a set of 100 people. This is what we want. And the formula for this is 100 factorial over 100 minus 5 factorial. And if we want to do it the easy way, we'll take our TI calculator and crank this out. I was under the impression that MyMathLab had some sort of a permutation function, but I just checked a minute ago and it doesn't look like they have one. So if you want to use your calculator on the homework, go for it. You're going to use it on the, the final exam anyway. Now, if you don't have the calculator handy, 100 factorial is 100 times 99 times 98 times 97 times 96 times 95 times 94. That's 100 factorial. And this thing, this is 95 factorial. So that's going to be 95 times 94 times ... 3 times 2 times 1. And this cancels with this. What we're left with is 100 times 99, 98, 97, 96. And that gives us, what, 9,034,502,400. Wow. This many ways of selecting 5 officers from a high school with a senior class of 100 students? Thank God they didn't have 600. Oh my goodness, this is a big number. If you want to take your calculator and do 100p5, go for it. And what we do, we type 100, we hit the probability button. And we're going to see NPR, NCR, and factorial. And NPR is already going to be underlined. So we'll hit enter. And what we're going to have is 100 NPR, and we'll type in the 5 and hit enter. This is a good one. The principal of Wood River Junction High School will be selecting 3 seniors from the top 5 ranking seniors and 2 juniors from the top 5 ranking juniors. The ranking is academic. So the principal selects 3 seniors from the top 5 ranking seniors, 2 juniors from the top 5 ranking juniors to represent the school in the state's model legislature. How many different groups of 5 representatives are possible? So we're going to select 3 seniors, 2 juniors, put them together in one group of 5 representatives. Is order a concern here? Of the top 5 seniors, 3 are selected, not necessarily the top 3 academically. Maybe just randomly, 3 seniors are selected from the top 5. Does the order in which those 3 get selected matter? No, they're just selected or they're not selected. So a senior from the top 5 is either selected or they're not. If they are selected, the order of selection makes no difference. The same with the 2 juniors who are selected. Order of selection doesn't matter. How many different groups of 5 representatives are possible? And you know, I smell a rat here. This is actually kind of a trick question because I just realized this is sort of an exercise within an exercise. This is one of those 2-stage problems. First stage, the first stage we select the seniors. How many different ways? The number of outcomes, let's see. We have 5 seniors and we're going to select 3 of them. Order doesn't matter. So this is a combination of 3 students selected from a set of 5. 5 factorial over 5 minus 3 factorial times 3 factorial. And 5 factorial is, I'll tell you what, 5 times 4 times 3 times 2 times 1. You know what? If you can use your calculator to do this, by all means do it. This is 2 factorial, 2 times 1. This is 3 factorial, 3 times 2 times 1. And let's see, these guys cancel with these guys. And the 2 here cancels with the 2 of one of the 2's and the 4. So, wow, okay, I guess there are 10 ways we can do this. Oh, thank goodness, small numbers for a change, huh? Well, the second stage, select juniors. Number of outcomes equals, okay, we're going to take 5 juniors and select 2, and the order doesn't matter. So this will be 5 factorial over 5 minus 2 factorial times 2 factorial. Three factorial times 2 factorial. Whoops, let's see. This is 3 factorial, so this is 3 times 2 times 1. This is 2 factorial, 2 times 1. And wow, these 3 factors cancel with those 3 factors, and the 2 here cancels with one of the 2's and the 4. Son of a gun, we get a 10 again. I'll tell you what. Let's use some of the terminology from before. First stage, number of outcomes, 10. So I'll write N1 equals 10. Second stage, number of outcomes equals 10. So I'll write N2 equals 10. Total number of outcomes is number of outcomes of the first stage, number of outcomes of the second stage. That's our counting rule. And that's just going to be 10 times 10, which is 100. 100 possible groups of 5 representatives are possible when chosen this way.